Alright, here's Spring 2022, Exam 2. Alright, for questions 1 and 2, we're looking at these two outputs, total and n. So looking at our program, we have this while loop, while n is greater than total, do everything inside. So, because it's a while loop, it's a pre-test, so we check the condition before we even start. We see that n, that large number, is greater than total, which is 0, so we can continue on inside the loop. So total plus equals n mod 100. Remember that any number mod 100 would be the last two digits. So in this case, it would be 59. And then n divide equal 10. Really all that is just taking off the last digit, so I'm just going to cross it out on the n. And then we're going to keep doing this again and again as long as n is greater than total. So we're going to do it again. Total plus equal the last two digits, so 35. This is going to result in 94. And then n divide equal 10. Total plus equals n mod 100, so plus equals 63. That's going to be 157. N divide equal 10. And now n is equal to 146, total is equal to 157. Therefore, n is not greater than total. We're not going to do this loop any more times. So, total is going to be 157, and n is going to be 146. So A and A. For 3 and 4, we're once again looking for total and n, but we have a different code setup. So, this do while loop means we're going to check the condition after we've already gone through it once, so we don't need to worry about that condition yet. So, if n mod 3 equals 0, that's saying if evenly divisible by 3, then do everything inside. 351 is evenly divisible by 3. It would be 117 with no remainder, so therefore we're going to do what's inside. So total plus equals n mod 10. N mod 10 is just going to be the last digit. Remember, 100 was 2 digits, 10 is 1 digit. So total plus equals 1. And then n divide equal 10, we're going to take off that last digit. Now, because we already did the first if case, we're going to skip over else if and else, no matter if they're true or not. Now we're going to check this condition. While n is greater than 0, n is 35, so we're going to continue on to the next iteration. Now, if n mod 3 equals 0, if it's evenly divisible by 3, 35 is not evenly divisible by 3, so we're going to go on to the else if case. N mod 2, this is basically saying if n mod 2 equal 1, because that would be true. So remember, any number mod 2, it's 1 if odd and 0 if false. So this is really else if odd. So is 35 odd? Yes. Therefore, we're going to do total plus equal 1. N minus equal 1. So now it's going to be 34. We're going to check n is greater than 0 once again and go back to the top because it is true. So this time, else, so we know that 34 is not evenly divisible by 3. It's not odd, therefore we're going to go to the else case. Total plus equals 2. N minus equals 2. N is still greater than 0, so we'll do this again. 32 is not evenly divisible by 3. It's not odd, therefore we go to the else case. Total plus equal 2. And n minus equal 2. N is still greater than 0, so we go back to the top once again. 30 is evenly divisible by 3, so we're going to do total plus equal n mod 10. Well, 30 mod 10 is going to be 0 because the 0 is in the 1 place, so total will still be 6. N divide equal 10 is going to be 3. Then because the if case was true, we skip the rest of it. So we go check n is greater than 0, which is true. We loop once more. 3 is evenly divisible by 3, so total plus equals n mod 10. Any number mod something bigger than it is going to be the first number. So 3 mod 10 is going to be 3. So total plus equals 3. N divided equal 10. 3 divided by 10 is 0. Int divided by an int. And now n is no longer greater than 0, so our loop ends. So we know that total equals 9 and n equals 0. So C and A. Moving on to questions 5 and 6, once again we're looking for total and n. So For n equals this number, n is greater than total, and n divide equal 10. So to start, we know that n is greater than total because total is currently 0. So we're going to do total plus equal n mod 100. Remember, this is the last two digits. Is it less than 50? If it is, we're going to do plus equals negative n mod 100. If it's false, we're going to do positive n mod 100. So is 41 less than 50? Yes, it is. So we're going to do the true case of this ternary operator. So we need to do total plus equals negative n mod 100. So total plus equals negative 41. Now before we go to the next case, we're going to say, is n greater than total? Yes, it is. So, and then before we got to this point, we'd want to do n divide equal 10. Sorry. So we would do this right here before we checked again. So now we're going to check, is n greater or equal to total? Yes, it is. So total plus equals n mod 100, which is 74. Is 74 less than 50? No, it isn't. So we're going to do total plus equals n mod 100. So that's going to be positive n mod 100. So that'll be negative 41 plus 74, which is going to be 33. And then now that we reach the end of the loop again, we're going to do n divide equal 10. So take off that last digit. N is still greater than or equal to total. So we're going to do total plus equals n mod 100. Is it less than 50? Yes, it is. So we're going to do plus equals negative n mod 100. So plus equals negative 27, which is going to be 6. Is our new value for total. And then n divide equal 10. N is still greater than or equal to total. So we do total plus equals n mod 100. Again, any number mod, a large number is going to be the first number. Is 52 less than 50? False. So we're going to take positive of n divided by n mod 100. So 6 plus 52 is going to be 58. And then n divide equal 10. So before we loop again, we're going to check, is n greater than or equal to total? Is 5 greater than or equal to 58? No, it isn't. So we're going to stop looping. Our final values are 58 for total, and it'll be 5 for n. Questions 7 and 8, we're looking for total and sum. So first we're going to look at total. So this one is really asking us, if you look at it all, the only thing we ever do is increment total, as well as x, y, z, of course. And so we're just going to look at how many times do we hit this line right here. So working our way outwards, we know that to go through the loop for z, we're going to have the initial value. Then we're going to divide equal 10. Until z reaches 0. Because remember, the condition is z is not equal to 0. So we know that once we get to this point right here, we're not going to actually execute the loop. We're going to stop right there. Now, working our way outwards, we're going to look at the while loop. So y equals 1 times equal 2, all the way up until it's no longer less than 30. And so once y reaches this point, we're not going to go through the loop body anymore. Finally, looking at the x loop, we'll have 1, 3, 5, 7, 9. Once we hit 9, we're not going to execute the body of the loop. We're going to stop. And so because these are all nested inside of each other, there's a relationship of multiplication. So if we execute the z loop, the body of the z loop, 5 times every time we hit that point, well, we know we're going to hit it that point every time that the y loop executes, which is going to be every time that the x loop executes. So it's really multiplication. So there's going to be 4 times for the x loop, 5 times for the y loop, and I'm getting these by counting all the numbers I wrote out, including the one that's crossed out, and 5 times for the z loop. Now we multiply it all the way down. 4 times 5 times 5 is going to be 100. Then to find the sum, well, the sum is going to be x plus y plus z. And so we're going to take the final values of these, which are basically the values that break the loop. So we're going to add together the values that I crossed out in red. So 9, 32, and 0 added together would be 41. It's important to remember that these are the final values. We do reach the values. Just because the condition says we end when we hit that point, we still have to hit that point first. So don't think that we end at 7, 16, and 5. We do hit 9, 32, and 0. We just don't execute the body underneath them. All right, for question 9, we're going to be looking at this function, trying to find the value of total at the very end. So, kind of going from the start, we have this value n in total, and we have a do-while loop right here. So remember, for a do-while loop, we don't care about the condition until we've already executed it once. We're guaranteed to do it at least once. Maybe we'll do it more if the condition passes, but always start it first and then check the condition at the end. So, total plus equals make calculation. We're going to pass n and n mod 2. So, down and make calculation, n equals 5, 3, 6, 4, 2. And start is going to be 0, because n mod 2 is 0. An even number, mod 2, is going to be 0, and odd number, mod 2, would be 1. So, int result equals start. So, well, n mod 10 is greater than 0, so while the last digit of n is greater than 0, we're going to do this switch case, and then decrease n. So, the switch case uses the value start, which we know is 0. So, result plus equals n mod 10. So we're going to do at 2, and then because of the break statement, we don't do the case 1. Then we subtract 1 from n. So that's going to become, I'm just going to cross out this last digit, and that's your new value for n. And then as long as n mod 10 is greater than 0, as long as that last digit is greater than 0, we're going to keep going. So again, we're going to keep going to the switch same case every time because start never changes. So case 0, result plus equals n mod 10. So it's going to be plus equals 1. And then n minus minus is going to change n to this number. Now the last digit is 0. So n mod 10 is not greater than 0. We break out of this loop, and that's the end of the function. We're going to return back result. So total plus equals 3. And then as long as n, and then we're going to do n divide equal 10. So we're going to get rid of this last digit right here. Now as long as n is greater than 0, we're going to do the same thing all over again. So our new parameters are going to be 5, 3, 6, 4. And because 5, 3, 6, 4 is even, start is going to once again be 0. Once again, we can go through and loop through every time, but you might have kind of realized what our pattern is. So as long as start is 0, we're just going to keep adding the ones place until we reach 0. So if you find a shortcut like this on the exam and you're confident, this is a great way to kind of gain back some time you can spend on other problems. So I'm going to do plus 4, plus 3, plus 2, plus 1. So now n, after all this, is going to be 5, 3, 6, 0. N mod 10 is 0, which is no longer greater than 0, so we end our loop. And we're going to return the result, which is going to be 10. So now total plus equals 10 up in main. N divide equal 10, so take off that last digit. Our new number for n is 536. Once again, n is greater than 0 in this condition right here. So we're going to go through and loop again. Our new parameter values are going to be n equals 536, and then 536 mod 2 is 0. So I'm going to use my shortcut once again. So plus 6, plus 5, plus 4, plus 3, plus 2, plus 1, and now n, after all this looping, is going to be 530. 530 mod 10 is 0, so the loop breaks, and we return back a result, which is 21. So in main, total plus equals 21. Our new value is 34. Then n divided equal 10, and our new value for n is 53. N is still greater than 0, so once again we go through our loop in the main. This time our parameters for make calculation, n will equal 53, and start equals n mod 2. Now we have an odd number, so an odd number mod 2 is 1, so start equals 1. Therefore result also equals 1. So, while n mod 10 is greater than 0, once again we're going to count through all the 1's places, but now we have a different case that we're doing. So, now that start equals 1, we're going to go down to this case right here. So, result times equals n mod 10, n minus minus, and then n mod 10 is still greater than 0, so result times equals n mod 10. Remember, we're going to go through the same case every time because the variable start never changes. So our final value for n is 50. 50 mod 10 is now greater than 0, so this loop ends. We return back this value right here, which is 6. Total plus equals 6, now it's 40. N divided equal 10, our new value for n is 5. So finally, our parameters for make calculation this time are going to be 5 and 1, because 5 is odd, so therefore start n mod 2 is 1. And because I just kind of figured out that pattern, I'm going to do the exact same thing. So 1 times 5 times 4 times 3 times 2 times 1. And then my final value for n would be 0. So I'm going to return back this value right here, which would be 120. So total plus equals 120. Total is 160. N was 5. N divided by 10 is 0. So this condition right here is no longer true. This do while loop ends, and we print out the total. So after all this work, our total value is 160. So you can see this problem did take a lot of time. You can spend more or less time depending on how comfortable you are. You can see that I went through several iterations to start, and as soon as I started picking up the patterns, I started taking these shortcuts. So if you have the confidence or you're running low on time, take these shortcuts. You can always come back and revisit in more detail later on. It's totally up to you and what you're comfortable with. But the main thing to recognize is that there's nothing in here that changes the value of start. So there's no need to reevaluate which switch case you do within one function call. Of course, when you call at a different time and the value of start as your parameter changes, the behavior may be different, but don't get caught up in this switch case right here. Question 10. Which of the following statements regarding the problem above is true? A, the logic of the program above includes nested repetition. So this one is going to be true. And it's a little tricky because you might not see the repetition right away. So we have a do while loop right here. Right there. We have a while loop right here. So these don't look nested, they look apart. But the key to realize is that really this while loop right here takes place inside this line right here. So if you substituted in the code of the make calculation function, upward is called in main, you would actually see the while loop inside of the do while loop. So therefore there is nested repetition. It's just kind of broken apart by the function structure. So A is true. B, the process being implemented using the do while loop is event controlled. So for this one, we're looking at this condition right here. So while n is greater than 0. So n is not some event that happens. It's not a user input or something else like that. All it is the counter. We have an initial value at the top. So we had this initial value, and then we just divide equal 10. So we know, just by looking at this code up here, that it's going to take 5 iterations to complete the do-while loop. It really doesn't even matter what happens in make calculation because it's not changing the value of n. So as long as that's the initial value of n, I know for sure that loop will happen 5 times. So it is not a event controlled. C, the number of times the while loop iterates is equal to the number of digits in the integer n. So if you understood how to do number 9 correctly, you should know that this is not true. We're looking at the do-while loop, which is in make calculation. And that loop through, the number of times it looped through is whatever was in the ones place. So don't get caught up. The do-while loop was the number of digits, but the while loop within make calculation was just the value held in the ones place. So C is false. Our answer is A. All right, for questions 11 and 12, we're looking at x, y, and z, these 3 ints, and we're going to see how they increase and decrease throughout the program. So there's kind of 2 main things to remember, is that we always want to keep short-circuiting in mind. The other one is that AND has higher precedence than OR. So this is easy to forget, but it's also easy to get confused. Higher precedence does not mean you do it first, necessarily. It's just where you still want to work from left to right. So don't get caught up in that. So I like to start by just going through and adding parentheses to everything with an AND, so I don't get messed up. So I'm just going to add every time I see them. These aren't really necessary because there's only an AND there. And then the AND right here. Remember, you can always find the precedence table in your back of the exam, which is great, especially if you forget, not operator has a lower precedence, anything like that. So solving this out, we're going to do if x plus plus and plus plus y. So first, x plus plus. Well, remember that plus plus afterwards, or a post increment, means we're going to increase x, but that's not relevant to what we're solving right now. So for the case of this logic, x is equal to 0 or false. So if the left side is false, then who cares what the right side is? For an AND, both sides need to be true, so we don't care what the right side is. We're not even going to look at it. So we don't touch y. Or z plus plus. So again, because it's a post increment, the plus signs come afterwards. We're going to look at what is z right now. That's all we care about. Well, z is 0, so that's going to be false. So we have false or false. That's going to be false. Now as a side effect, we looked at x plus plus, we looked at z plus plus. So those 2 values are going to increase. Remember that we never actually looked at y, so we're going to ignore that increment. Now because this all simplified down to false, we're not going to look inside of the if body, we're going to move on to the else if case. So again, don't get confused here now that we're looking at line 13. We give higher precedence to the AND, but we're still going to look at the left side of the OR first. We're going to work from left to right. So minus minus y. Those minus signs come first before the variable, which means we want to decrease it before we even consider what's going on. So before I touch anything, now y is negative 1. Remember that any value but 0 is going to be true. So this is true. Now because the left side of the OR is true and only one side needs to be true, who cares what happens on the right side? We're going to totally ignore it. So else if true, z equals y or greater than x. So z equals negative 1 greater than 1. Well, this is false. False simplifies to 0. So z equals 0. Because we went into the body of this else if, we don't care about the other else if, we don't care about the else. So we have our final values because we've gone through the whole construct. X is going to be 1. Y is going to be negative 1. And z is going to be 0. Moving on to question 13. which of the following logical operators has only one of its two operands evaluated, such that the operator short-circuited in the code segment above? So, well, where do we do some short-circuiting? We know from before that there was a short circuit here. We didn't evaluate the right side. And there was short-circuiting right here. We didn't evaluate the right side here either. So that would be the AND on line 9 and the OR on line 13. This question doesn't say anything about line 13, so the answer is going to be B, the AND on line 9. Question 14. Which of the following statements regarding the usage of the switch construct is false? A. Each switch case label is the keyword case followed by a constant expression. This is true. You can't have a variable. It needs to be some constant value, whether that's a hash-defined value, a char, or an integer, something like that. B. Each case label represents an integral value that is a possible result of the control expression. Again, this is going to be true. Remember, integral means of the integer family, so it can be an integer, a long, a char, anything like that. And it's something that could match the control expression, the variable, or whatever you're trying to match up. So true. C. No case label may consist of an expression with multiple mathematical operators. So this one is going to be false. You can have mathematical operators if you're using all constant values and it simplifies down to an integer. So it's okay for your case to be 9 divided by 3. But you can't be int x divided by 3 because x is changing, or at least it can change. And so your case, the values corresponding to each case need to be a constant value predetermined. So C is false. It's a little bit of a weird one. I don't know when you necessarily want to use it, but it is allowed. All right, now we're going to look at questions 15 and 16. For this one, I'm just going to dive straight into the code, but we'll be looking at the printed data and result. So looking at our program, we start off by setting up this data line. We're going to call count direct with x as our parameter. So down at indirect, n equals 10, because that's what x was in the main. If n minus minus is greater than 0, so remember that n minus minus is a postfix decrement, which means we're going to consider the logic, finish out solving the line of code, and then as a side effect we'll decrease it, but that's only after everything else is done. So if 10 is greater than 0, which is true, now we're going to go inside. So here comes that side effect. Now n equals 9. Printf n, so we're going to print out 9. And now n equals count direct, passing 9 as the parameter. So we can see there's some recursion going on now as well. So now we're going to solve this function with n equals 9. So, and I'm going to just keep a little side tab. So, in the first time this function is called, n equals 9. Now we're in the second layer of recursion. So, n equals 9. If n minus minus is greater than 0, again, 9 is greater than 0. As a side effect, we'll decrease. We're going to print out n, and we're going to call this function again with 8 as our parameter. So 8 is greater than 0, decrease to 7, print out 7, call this function again with 7 as our parameter. So now we're in the fourth layer of recursion, or fourth layer of calling the function. So 7 is greater than 0. As a side effect, we decrease. We're going to print out 6, and then we're going to call this function with 6 as a parameter. We're going to keep doing the same thing. All the while n minus minus is greater than 0. So we're going to kind of keep seeing this pattern. If you can pick up the pattern, that's going to save you a lot of time. All right, so I'm going to jump ahead to this iteration right here, or this level of recursion. So when we're on the 9th call to the function, we're going to pass in n, which is 2, as our parameter. If n minus minus is greater than 0, yes is true. We're going to decrease as a result, print out 1, and call it again. So now n equals 1. If n minus minus is greater than 0, remember that it's a postfix decrement, so we care about 1 is greater than 0, which is true. We decrease to 0, but we already checked the if statement, so we're going to go inside. Print out 0. Call this function again with n as our parameter. If 0 is greater than 0, nope. But as a side effect, we're still going to decrease it, so now n is negative 1. We're going to return n. So now remember that every single time we call this function, we said n equals this. So in this table, I've been storing the values of n. But now we said that n equals the result of call 11, n equals the result of call 10, and all the way back to the very beginning where we say x equals the result of count direct. So x equals negative 1. So moving down here, we can see that data goes from 9 to 0, and result equals negative 1. This is another problem where if you can pick up the patterns, it's going to speed things up a lot. Really say, you can recognize that there's a pattern of decreasing by 1 every time, and you know that the if statement is not going to pass anymore when you're around 0, 1, 2, negative 1, negative 2, around that zone. So skip a bunch of the iterations by using your shortcuts, and then when you think something's going to change in the behavior of the program, start going through by hand again, which is why I stopped when n equals 1 or 2. This will save you a lot of time, and if you ever feel uncertain, you can always come back later if you have extra time, but it's not worth getting caught up in every single iteration just for one exam question. Question 17. Which of the following statements regarding for loops is false according to course standards? A for loop should only be used with counter-controlled processes. This one is true. We don't want to do anything event-controlled, so no input validation or anything like that with a for loop for this course's standards. The for loop has 3 parts, and so to promote good practices, I want you to use the initialization, update, and condition every time, and use it as a counter type of loop. B, the loop control variable can be declared and initialized in the first expression of a for loop. This one is going to be false. So your loop control variable does need to be initialized, declared and initialized somewhere outside of the for loop, so really at the top of the UDF or main function. This is just, again, case for this course. You might have seen other things in other versions of C or other languages you have done prior. But with our version of C and with the course standards, this is the requirement. So B would be false. You cannot do it inside the for loop. C, make use of all 3 expressions when implementing a for loop in your program. Like I said, we don't want to do event controlled. We don't want to do anything where you skip one of the 3 parts. This course is teaching the fundamentals. It's promoting good practice. We don't want you getting lazy or using, different tools for things they're not really intended for. And so we want you to use every part properly. And so C is true. All 3 parts are required. Therefore, answer is B. 18. Given the following logical expression, which of the following logical expressions is one possible complement of the logical expression above? So we get to use a bit of De Morgan's law with this. So how I like to do this, break it down bit by bit. So what is the opposite of less than? Well, the opposite of less than is greater than or equal to. Remember why we use the equal to is really important. So the complement needs to, basically what it needs to have is that nothing in the original is in the complement. But when you put the 2 groups together, you cover all possible values. So if you said the opposite of less than is greater than, now you're excluding the possibility that x equals a. And so your complement needs to hold or contain every possibility that's not in the original. That's why I use greater than or equal to. Or becomes and. Greater than becomes less than or equal to, like I just talked about. And becomes or. Then not equal becomes equal. And then here's the trick where it's going to be really easy to get mixed up. So remember that and has higher precedence than or, which means that that part is kind of grouped. In the original, there's some parentheses right here. You don't need them because of precedence, but that's kind of the easier way to understand it. So in your final result, you need to have parentheses here as well, because you still want that part to be grouped together. Even though it's a complement and now you have an or, you want it to be grouped together, and it no longer has that benefit of precedence making sure that happens. So anything that was an and originally needs to have parentheses in the result. So in this case, you can see our answer is going to be none of the above. It is important to remember that your logical expressions, there are kind of some different ways to do it by throwing in knots and stuff. So you want to look at every answer choice, even if they don't match up. But in this case, none of the answer choices match what we're looking for. Question 19. Which of the following statements regarding selection is true? A. Conditional expressions cannot be nested. This is going to be false. So you could say, if, x is greater than 3. Sorry, I'm using the wrong type of brace there. Do this, blah, blah, blah. And inside you could say, if y is greater than 4, I want you to do this. And you can nest it as deep as you want, which is especially true when you start getting into function calls and stuff. You might have some pretty extreme nesting going on. So there's nothing against this, totally allowed. So A is false. B, the dangling else logical error can be corrected by indenting the if and else the same number of spaces. So this is going to be false. For C, we have course standards, of course, on how you should indent things, but the indentation means nothing to the compiler. It's not going to fix anything. It's not going to change how it even works. It might help you visually see what the issue is when you're reading the code, which is why there are course standards around it. But it has no purpose when it comes to the actual compiler. This isn't like Python where you might get confused. So B is false. C, the condition of an if-else construct must be enclosed in parentheses. So this one is going to be true. By the course standards, you must have everything inside parentheses. Which of the following statements regarding random number generation is false? Each call to the rand function returns the next integer in a series of random numbers. This one's going to be true. So I like to think of, some vast space of a bunch of different tables and numbers. And so your seed selected one of the tables. And so every time you call rand, you're just pulling the next row of that table. That's really all it is. And then, of course, rand is an integer, or returns an integer. B, the srand function must be called only once for each desired series of random numbers. This one's also true. So when I talk about this, vast space of, millions of tables that you could choose from, your srand is kind of selecting that table and pulling it out for you. And so if you keep going back, calling it multiple times, you're going to keep pulling the table and resetting to the top. And so you're going to get the same random value every time, which is not probably what you want to have, of course. So B is true. srand should only be called once unless you want to change seeds or reset your table. C, a call to the srand function includes the seed value as a parameter. This is true. If you wrote srand yourself, this is what your declaration might look like. So the answer is D, none of the above. All three are true. 21. Which of the following will generate a random number in the range from x to y, inclusive, where both variables are positive and y is strictly greater than x? So all this is asking for is our standard random number formula you should know from labs. So hopefully you recognize B as your answer. But if it doesn't jump out to you right away, this might help make it a little bit more clear. So y equals max. Remember, y is greater than x. X equals min. So you're going to say rand mod max minus min plus 1 plus min. So max minus min plus 1 is your range. Don't forget that plus 1. If you kind of forget about why it's there, let's say you want to choose a number from 5 to 10. So you could have 5, 6, 7, 8, 9, or 10. That's 6 different numbers, but 10 minus 5 is only 5. So because of that inclusive keyword, you have to add in 1 to your range. And then adding your min or adding x is just scaling it or shifting over your range to the right place or right range of numbers that you want. So B is the correct answer. That's a great formula to just memorize. You might see, different exam questions replace the variables with different names, but it's always going to look exactly the same. All right, question 22. Which of the following statements regarding repetition is false? A, the initialization of a loop control variable must take place outside the body of a pretest loop. So we have two types of pretest loops. We have the for loop and the while loop. So for the while loop, all you do is you check the condition and then you jump into the body. So you already need to have that the loop control variable initialized somewhere, in main, earlier in the UDF, whatever. But it already needs to be initialized so that you can make that comparison. There's no chance to initialize it at that point, so it needs to be outside of the body. Also because you're checking the condition before you actually get to the body, the more important part. So you need to have something to already check. Now for a for loop, you actually initialize, regardless if you've already initialized the variable before, you set it to some value in that first line of the for loop. Your for loop looks like this. You're already initializing it right here. Remember, this is not part of the body. The body is what's inside the curly braces afterwards. So you've already initialized at that point, if you haven't already earlier. So A is true. B, the number of times that the loop control expression is evaluated is one more than the number of iterations in a post-test loop. So this one is going to be false. It would actually be one less. So if, let's say, this is our program. So do, we're not going to check the condition. We're going to go inside. So basically, body, cond for condition. So we're going to do the body. We're going to not check it yet. Did the body. I++, now I is 2. Is I less than 5? We just check condition. Because it is, we're going to do the body again. We're going to go back to the top. Do the body. Is I less than 5? Yes, it is. Just check the condition. Do the body. Is I less than 5? Yes, it is. Do the body. Is I less than 5? No, so we end. So actually I misspoke there, but it would be the equal number of times. Sorry. So not one more time, but equal number of times that you check the condition and execute the body. Which would be the inverse of a pretest loop. You would check the condition one more time. C, so B would be false. C, it is possible for the update of the loop control variable to be part of the loop control expression of a pretest loop. This is going to be true. So remember your loop control expression. You have this for loop right here. You also have a while. Let's say I is less than 5. So, taking this that we already have on the left for that do while loop, well, instead of having the I++ inside, let's say we have a while loop and we say I++ is less than 5. So now we're going to see if that counter is less than our endpoint, and we're also going to increase it at the same time with that postfix increment. So we can do both for that while loop, which would be a pretest loop. So C is true. All right, question 23. Which of the following may be an indication that the incorrect looping construct was selected for a repetitive process? A, identical logic found both inside and outside the body of the loop. So usually this means you do some chunk of code, and then you have a prefix loop with essentially the same code inside of it. There's other ways that you can kind of mess with the looping, but this is the most often thing that I encounter. And really, this typically means you just need to use a postfix loop instead, because you're trying to guarantee that it happens at least once. So that's the kind of a behavior of a postfix loop. So instead of, essentially hard coding the first iteration outside of the loop, just use a postfix where it's guaranteed to happen once, your do while loop, and then you'll check and go back and repeat. So A would be true. B, the loop control variable is initialized to a value that guarantees at least one iteration. So this is not really talking about like a for loop. Like if you have a for I equals 0, I is less than 5, or you just want to have 5 iterations, that's not a big deal. But if you're just, because you know how many iterations you want to have. But if you're trying to guarantee, something that's based off of a function result or something where you don't know the number of iterations, then this becomes an issue. Again, it's usually using a prefix loop when you want to have a postfix loop to guarantee at least one iteration. So A and B are correct. C, multiple logical operators are part of the loop control expression. There's nothing wrong with this. Typically you'll see, your I is less than 5, I is less than n, whatever, but it's totally fine to have complex control expressions. Maybe you're doing, have a maximum number of iterations, or when a function returns a certain value, something like that. Totally fine. So A and B would be the true answers. So our answer is D, both A and B. Question 24. Which of the following is the output generated by the program above? So looking at both grade 1 and 2. Jumping right in, grade equals get grade, 84. On line 9, we're going to call the function at line 18. Score equals 84. Pass equals -1. For the switch case, line 22, we're going to use score plus 7, 84 plus 7, or 91, divided by 10. 91 divided by 10 is 9. Remember, int divided by an int, we don't care about the decimal. So, case 9, pass equals 1. Then we have a break statement, which means we ignore everything below in the switch construct. We're done. We get down to the return line. That's going to be return A minus 1 plus 1. These cancel out, so we're just going to return A. So grade number 1 is A. Then line 12, grade equals get grade 68. So we're going to call this function again. Line 22, 68 plus 7, 75, divided by 10, 7. Case 7, pass equals 3. Return A minus 1 plus 3, should just be A plus 2. So remember, all the values on the ASCII table are in alphabetical order, so you don't even need to look at that table. A plus 2, just add 2 letters, you're going to get to C. So grade 2 is C, therefore our answer is A. Grade 1 is A, grade 2 is C. Alright, question 25. Which of the following is the output generated by the program above when both of the break statements, line 26 and 28, are removed? So, if you remember, the first time we called this function, our case was 9. So when we're looking for grade number 1, case was 9. Grade number 2, case was 7. So this question is asking, if we took out this line right here and this line right here, what would happen? So remember that when it comes to switch cases, you just keep going until you hit a break. That tells you to stop, reading down the list. So because these all are changing the value of pass, all we really care about is what is the very last statement. Well, the very last statement is this one right here, because anything that happens above, anything that happens here is going to get overwritten by this value, 3. And we know from grade number 2 being case 7 that when pass equals 3, it returns C. So without those break statements, both grades would be C. Actually, any grade you put in would be C, unless it was not high enough to reach one of those cases. All right, for questions 26 and 27, we're looking for the values of y and z. So when I'm using an array, I'm going to substitute in my defined constant, make sure I have 7 values, and leave the array indices so I don't get confused about C using zero-based indices or arrays, not one base like MATLAB, some other languages. And looking at my code, I can see this is kind of confusing. What are these ternary operators doing? I'm going to loop through it a lot. So in this case, I'm actually going to find that it's easier to find the English translation first before I even do any calculation. So looking at this first line right here, we're going to first compare the value at the I index to the Y index. If the one at the I index is less than the one at the Y index, we're going to assign Y to I. Otherwise, we're going to assign Y to Y. So if x of I is less than x of Y, Y equals I. I'm not going to worry about the other case because that's not actually going to change the value. So again, kind of English, kind of code, but it's a little bit easier to read. For this one, down below, we're going to look at x, or in x, we're going to look at index size minus I minus 1. So remember, size minus 1 is going to be the last value in the array. So then minus I, every loop iteration, we're going to go 1 to the left. But we're going to start with the rightmost value. If that's greater than z, update z to that value. Otherwise, z stays the same. So if x size minus I minus 1 greater than z, which is the same as saying x of 6 minus I greater than z, z equals x6 minus I. So this is a whole lot more readable than what we had before, and because we're going to be looping through several times, it'll make this part go a lot faster. So you can do this before you start a problem, or you can start going through and just see if it's even worth getting to this step, but it'll save us a lot of time. So, starting with I equals 0. So, we're going to look at x of I, so x is 0, which is 93, x of y, which is 93 because y is also 0, and y is going to equal I if x of I is less than x of y. Well, it's not less than because it's equal to, so nothing changes, y stays at 0. Then we look at x of 6 minus 0, so x of 6, which is going to be, oops, sorry for that mistake right there, that should be a 6, not a 7. So x of 6 is going to be 38. If that's greater than z, which is 0, then now z is 38. So z is 38. Now I equals 1. So we're going to look at the value at index 1 compared to the value at index 0. The one at the index 1 is less than the one at index 0, so we're going to update y to I. So now y equals 1. Now we're going to look at x of 6 minus I, so that's going to be x of 5, 72. Is 72 greater than z? Is it greater than 38? Yes. So now z is going to update to 72. Now we can update I to 2. We're going to look at index 2, the value 84. Is that less than the value at index 1? Yes, it is. So y is going to update to 2. Then we're going to look at the value at index 6 minus 2, which is 63. Is that greater than z? No, it isn't, so z is not going to change. So we're starting to see some more patterns. We could even kind of break this into more shortcuts if we wanted. So what are we really looking for? If x of I is less than x of y, we're going to update to the new one. So every time we get to a smaller value, we're going to update y to that new index. So really, we just need to find the smallest value, which is going to be 38. And we know that no matter what happens before then, when we get to that point, 38 is going to be smaller than whatever is located at index y. So y is going to have to update to index 6. So we can just say y equals 6. We don't have to go any further. We found the pattern, we can kind of shortcut through the rest. So B is our answer. Now for Z. Z is saying that if we find a new higher number, we're going to update Z to that new high number, or the maximum number. So we can see that we updated Z, every time from 38 to 72 to 63, 72, or not to 63, but to 72, 84, 90, 93, all the way to the maximum value. Z equals 93. We can take this shortcut because we know we're going to go through the whole array, because we have I equaling the values from 0 to 6. So it's not an assumption, it's something we know to be true. And so now we skipped all that work, and if you wanted to kind of jump to this point earlier reading the program, that's totally okay, but it never hurts to just run through a couple iterations to be sure. So our answer for 27 is C. Question 28. Which of the following for loops will correctly iterate over every element in an array of size 5? So really all we're looking for is which one will execute 5 times. So just writing out the possible values of I, we have 1, 2, 3, 4, and then at 5 the loop would break. For B we have 0, 1, 2, 3, 4, 5, which will still work because it's equal to 5, and at 6 would be when it breaks. C we have 0, 1, 2, 3, 4, and then 5 would break it. So C is the only answer that has 5 different iterations. So we could do something, some sort of calculation on every value in the array. So C would be the correct answer. 29. Which of the following is a valid use of a fixed length array X of size 5 in the C language? A. Display all values in the array, which is shown on the right. So printf %d x. So remember that an array, the x itself is really just a pointer to the first value. And so if you've used pointers and functions, if you practice with this, you would know that you'd have to use star x, and even then that would only point to the first value in the array, not to displaying all the values. So for one thing, this is already wrong, and two, you would have to use a loop to actually hit every value. So A is not valid. B, copy all values from the array x into array y of the same size. Y equals x, you cannot do that. Even though they're the same size, again, you're you're not copying the values, you'd be actually changing the address to reference the same array. So it would not be a copy. Any edits you make with one variable, you'd be editing the other. C, add a new element to the end of the array. So x of 5 equals 0. Remember that x of 4 would be the last value in that array because we start at 0. So x of 5 doesn't exist. It could just be a blank space of memory, but it could be used by another variable, most likely the variable you declared right after declaring the array. And so you could start overwriting some other value that you use in your program. So suddenly when you have, int z is something that you don't expect it to be, it could be because you went beyond the bounds of the array you declared right above. It's not a guarantee, but it is likely to happen based on how the compiler sets up your program. So D, none of the above. None of these are valid ways to use a fixed length array. 30. Which of the following statements regarding arrays in the C language is false? A. Values in an array are stored consecutively in the memory of the computer. This is true. So if you have an array of size 5, 5 ints, they all should be back to back in the memory. Certain variable types might have some different compiler optimizations, but we generally assume that they're going to be back-to-back. B, when used throughout a program, an array's name represents both its starting address and its size. So this one's going to be false. The size is not kept with the array name, and so you can't just say, from start to end. You have to actually hold on to that size with some sort of variable, defined constant, something like that. So B is false. C, all elements of a given array share the same data type. This one's true. So when you declare an array, you might say int bracket. You might say, double star, referring to an already created array or a malloc array that you'll learn about later. But all these arrays are going to have the same data type for every variable within. So the answer is going to be B. Question 31. Which of the following is not a valid function declaration for the function UDF? So, looking up here, we have it void UDF with an array of integers called y. So, it returns void. Obviously, all our answer choices have that. This would be totally fine right here, B, because it matches perfectly. We, of course, do not have to actually use the name of the variable. We can just have the type, just like with a regular function declaration we've been doing without arrays or pointers, anything like that. So this would be totally valid as well. A is also valid. There is nothing binding the UDF to actually limit the array to size 5, but it's totally fine to have in your declaration. Therefore, the answer is D, none of the above. Question 32. Which of the following is the correct way to call UDF with the array x as the only argument on line 8? So, for this one, the answer is going to be C, just by definition. But basically, you're not, you're not declaring what type of variable it is. So just like we would say, something like star pointer. And then later we would, do something with a pointer. Even if it's not in this class, we might say, pointer equals some value, blah, blah, blah. So this star does not carry down with the pointer unless we want to actually dereference it. But it's the same thing with an array. So the bracket notation, the size with it, helps us declare what that array is. But we don't carry that notation with it because it's only useful in declaring it. So it just keeps the name x throughout the rest of the program. So the answer is going to be C. 33. Assume the correct function call described in problem 32 is added. What is the output generated? So going up to our code. All right. So we're going to say so y bracket is going to be the same as x bracket. Int I, we're not initializing, but then for I equals 1, I is less than 6, plus I. So y of I times equals y of I minus 1. So rewriting our values down here for y. And then our indices below. So y of 1 times equals y of 1 minus 1, or 0. So 5 times 6 is going to be 30. Now I is 2. So y of 2 times equals y of 1. It's going to be 120. I equals 3. Y of 3 times equals y of 2. I is 4. and so on, all the way to the end. We can just kind of see what this pattern is until we reach the end of the array when I equals 6 and the loop breaks. Then we go back to main, we print out x of 5. X of 5 is going to be this number right here, so our answer is C, 720. Given the following arrays declared in the local declaration section of a function, int x of size 5, int y of size 5 equals 1, what are the values of x of 0 and y of 1? So, first looking at x, we don't give it any initial values, so we don't know what that array holds. So, x of 0 is uninitialized, which means we can eliminate, well, I guess maybe not D, but we can eliminate C. Don't make assumptions about the value of any uninitialized variable, whether that's an array or a regular single value. However, the y is a little bit different because we did start giving it initial values, we just never finished giving the rest of the array. So, y of 5 is really the same as saying 1, 0, 0, 0. So there's just a little trick to know that if you start giving values to an array but you don't finish all the way to the end of the array, the rest of them will be set to 0. You can make that assumption. So therefore the answer is A. X of 0 is uninitialized, you don't know what it is, but y of 1 is 0 because the compiler will fill in the rest with zeros if you just do part way initializing.